so people don't get mad at me for not posting our discussion. But anyway, I think this is around where we left off. I know we left off those activities that you were going to take a look at last time, but we can do a quick review and start maybe at this plate. And I've been working on reorganizing the PowerPoint, so cleaning them up, trying to make them a little more understandable. So you might see some differences from the plates that we discuss now and the ones online. So for this plate, this is a typical table of reduction potentials that you might find in your textbook or online. And these come out of experimental results from labs uh, in the whole world that use the standard hydrogen electrode as um, the standard. So they define that having zero potential, much like we define sea level as having zero in height. But if we, that's not absolutely true because we could have measured from the center of the earth. And so, you know, sea level wouldn't be zero, it would be some number. But anyway, that's arbitrary. Once we pick a standard and everybody agrees on that standard, then you can measure everything relative to that and get measurements relative to the standard. But that also implies that you have meaningful differences from anything in that table. So if I look at the reduction potential, say, of copper, and I look at the reduction potential of zinc down here, whatever their values are in whatever standard you pick, that difference between those values is always going to be 1.10 volts, independent of where you pick the zero, because it's just going to slide this whole scale up or down. But those differences are the things that are going to remain the same. And those differences are what we're interested in. For batteries, for example, um, voltmeters measure the difference in potential from one electrode to the other electrode. And so that's why these tables are so powerful. You don't have to go and build your batteries every time to see what the voltage potential is going to be between them, because you already have these tables and you can use the tables to find that difference. Uh, so that's what's done. And when you do a table, for example, as reduction potentials, it turns out that this is also a ranking according to which half cells would um, tend to be reduced versus those which tend to be oxidized. So this is also a ranking. So the guys at the top are the ones that are most likely to be reduced. Okay. And when you match up one half cell with another, electrons flow spontaneously. And this tells you which way the electrons would flow spontaneously between any two half cells in this list. So these guys at the top they tend to be reduced. The guys at the bottom tend to be oxidized. So anything that's above anything else gets reduced. The thing that's below gives up the electrons and is oxidized. But we rank them all in this form as reductions. And so as reductions, we show the electrons as reactants, and the species in that half cell that's being reduced is going to add those electrons to it and form the species on the right. If we wanted to look at this reaction, um, from the perspective of the products, we could do that and say that the product um, could possibly form electrons and a species on the left. That would be oxidation. And so another way to look at this is by saying, well, okay, well, this must be true in taking these reduction potentials and relating them to oxidation potentials. So the thing, that species that gets reduced has a reduction potential, and it's related to the thing that it produces. And if we look at the back reaction, that thing that's reduced can be oxidized going the other way. So I could take electrons from that, and that potential would be the oxidation potential. And so it goes either way. We can rank them according to reduction in a chart like this, or we can turn the table around and flip the reactants with the products and rank them according to oxidation. And if we did so, we'd have to put a negative sign to all these values. That would take the one that's on the bottom and bring that to the top. And that's what happens. So now we have a ranking essentially according to the propensity to be oxidized, with the ones on the top preferentially being oxidized by anything below it. Uh, Now we don't usually use this because you only need one table or the other. It gives the same information. So someone picked to just use the reduction chart. But if you remember back in Chem 200, you had something that was called an activity series. And in the activity series, they ranked them according to oxidation. So the things that most likely were oxidized, those metals that were more likely to be oxidized, were at the top of the activity series because they were active. Metals tend to lose electrons, so let's rank them according to their ability to lose electrons. So the activity series is more um, in line with the oxidation ranking. But anyway, that's not that important. It's just, another piece of the puzzle in case you were wondering. So when we look at these rankings, uh, most of the time in the textbooks, like I said, you're going to see them ranked as reduction potentials. And we also use this terminology of agent, you know. So you'll see this use. So something that's an oxidizing agent itself is reduced. So if I have a ranking according to propensity to be reduced, then the strongest oxidizing agents are going to be on the top of this list and on the left, because it's always on the left that things are being reduced in this table, because um, the electrons are reactants. Okay, so these species are the species that are being reduced, that are on the left. Okay, now if I wanted to use this same table to look at the strongest reducing agent, then that's the thing that's most likely oxidized and gives up its electrons to reduce something else. Then I would be looking at something on the bottom of this ranking and on the right side, because these things on the right side are being oxidized. So there's a lot of stuff to unpack, and a lot of stuff that's going on with these rankings. Uh, what they're used for commonly in electrochemistry is simply to tell you um, if you build a cell, a voltaic or a galvanic cell, and that's a cell that runs spontaneously, so the delta G is zero, I mean negative. Um, what it tells you in this ranking is which way the electrons are going to flow spontaneously through that wire when you set up an indirect redox reaction. And then you can tap into the free energy of the flow of the electrons and run motors or lights or something like that. So um, that was a kind of a review of a lot of the topics that we've talked about. Did that spark any questions on anything uh, on your mind? Do you have any questions about anything that we talked about so far? Okay, so you're becoming electrochemistry experts. Let's see, get rid of that. All right, so we went on to look at the She, the standard hydrogen electrode. That's the one that they define the reduction potential as being zero. So this really should be 3 lines, not 2. This is the cell written as a reduction. So you have the electrons on the left, and you have the product H2 gas, and we know it's being reduced because the oxidation state goes from +1 here to 0. So the oxidation state is reducing, it's going down. Also notice that it's at 1 atmosphere pressure for the gas and 1 molar for the solution. That's what this superscript 0 signifies under standard conditions. So also you'd have to add 25 degrees Celsius to that. All right, this explains something that we already talked about, you know, how to figure out which half cell is going to be spontaneously reduced with electron flow into it, and which half cell is spontaneously going to contain the oxidation and the exodus of the electrons from that half cell. And so not only do we talk about that with the She, but once we establish our standard with everything, it's also true with any half cell in that list. It turns out that there's 2 handy dandy equations that are used to figure out cell potential differences, neither which you need, but you need to understand them because they're often used. If I want to find the cell potential of any 2 half cells, I just, take one number and subtract the other, and I see the difference. It's like finding the difference in height of 2 things on Earth. One is above sea level, the other one is below sea level. And so you just measure out that distance, and it's 1.10, but the units here are volts and not meters. So it's not a distance, it's a potential difference. And so, you can do that by just looking at the chart, or you can use this equation. Now, in this equation, note they use reduction potentials, even though at the anode there's oxidation, but we're going to use the reduction potential, even though we know that the redox reaction, the oxidation reaction to be specific, is that where zinc metal is oxidized to zinc 2 plus, but we're going to use the reduction potential of zinc 2 plus. But the reason why we can get away with that in this equation is because we put a negative sign here. So we inverse the sign of that reduction potential because it's supposed to be an oxidation potential. But, you know, like I said, you can get that potential difference by just looking at the chart. So this value is 0.34 minus this value is a negative 0.76. So it's negative, negative. That's a positive 0.76 plus 34 is 1.1. The advantage of using this equation is that you just pluck the reduction potentials right out of the reduction potential table and just put them in there and get the answer. Now, sometimes you'll see this equivalent equation that gets you the same answer. Again, they use the reduction potential for that cathode because that's where reduction happens. But now they add to that the oxidation potential of the anode. And so we know from this relationship that the reduction potential is related to the oxidation potential. So you get the same answer here, 0.34 plus 0.76 equals 1.1 volts. So you can get it with either one of these equations, and that corresponds to the voltmeter reading that you're going to get in lab, and this is under standard conditions. Any questions on that? Okay. This next plate that we talked about last time is more of some of the things that we already talked about. I think I said I'd let you read that. Any questions at all about this plate? Okay, so we did talk about that kind of stuff, and now we get to this activity. And so I was hoping that you guys would have a chance to take a look at this a little bit. And so let's look at each one. Activity 1, they want to know, is this reaction spontaneous? What do I need to do to find out whether that reaction is spontaneous or not? Anybody know? What could I do or what should I do to find out if that reaction is spontaneous? Okay, let me ask you this instead. Um, what parameter, I don't want to give it away, what parameter would we calculate to see if any process is spontaneous?
That's negative.
I'm sorry, what?
It's negative.
Yeah, what's usually negative?
Is
Do
it
you
the
remember what that thermodynamic property is called?
entropy?
Okay, but entropy. Okay, good. Entropy, remember delta S of the universe has to be greater than 0 for spontaneous process, right? Where did you hear that? It's only the most important law in thermodynamics and maybe even science. That's the second law of thermo, remember? Okay. Now, how does chemists, we don't usually talk about the change in the entropy of the universe. What do we talk about for chemical reactions as far as spontaneity? All right, I'm going to have to pull some teeth. What are our thermodynamic parameters? What are some of the quantities we look at in thermodynamics? What's important?
You got like phase changes in temperature?
Ah, good. Temperature is one of the important parameters. What other things do we talk about in
Particle
thermo?
size?
That's more kinetic, right?
Yeah.
What do these chemical reactions, like this one here, um, what are some of the parameters? Like thermo, what do you think about when when you hear thermo?
Heat,
Heat. What's the parameter that we use in chemistry to signify heat?
a phase change.
Yeah, the phase change is a process from liquid to solid or solid to gas or something like that. But what is the parameter connected with heat called?
The enthalpy.
Yes, enthalpy, H, or we're concerned with the change in heat content, delta H, right? From going from reactants to products. What other thermodynamic quantity? Delta H,
Q?
Q, yeah. So Q is heat, and that equals delta H under constant pressure uh, conditions. So these two are related to each other. All right, what else? Delta H. If I tell you, you're going to kick yourself.
What the change of E? Like the change of heat?
Yeah, the change in the internal energy, E. All right.
Delta G,
Delta G, what's that?
a free energy.
Yeah, that's the free energy, Gibbs free energy. Why do they call it free?
Because it's the deciding factor.
Well, no, because it's for free. Yeah, because it's given off. Now look, when a battery is connected with that wire, that flow of electrons is spontaneous. So it just flows and it's free. There's free energy. You can, put a light bulb in that wire and it'll light up, or a motor. You just have to tap into it. Okay, so all right. Now we have all of these, and we got delta S up there. So delta S is one for thermodynamics. Now the three um, energies that we use mostly in thermodynamics is delta H, that's exo or endothermic, that's heat energy. Uh, delta G is the Gibbs free energy. That's how much energy could be given off and can be used. It's often related to another term that we use a lot, work, maximum work. It's the upper bound. You can never totally convert all of that free energy into useful energy, because some has to be wasted, and you lose some in the friction and heat loss and so forth. And we spent a lot of time on entropy. So I'm going to go back to this activity 1 and ask, what could we calculate to see if this reaction is spontaneous? Any ideas? Is there a parameter we can calculate that's going to tell us, for this reaction in any process in the universe, tell us whether it'll take place spontaneously, or maybe the reverse will take place spontaneously? Any one of these? What do you think, guys? Let's go around the room. All right, I'm going to pull up this thing here. Francesca, you're just number 1 here. What do you think? Are you there?
Yeah, I'm here.
Are you busy?
A little.
Okay. All right. You want to get skipped?
Sure.
Okay, sorry. How about Lindsay? What do you think, Lindsay, out of all of these parameters?
Can you repeat the question?
Yeah. We want to look at the spontaneity of this reaction. So what parameter out of all of these do you think we could calculate to tell us something about the spontaneity of the reaction? Do you have your, yeah, go
I
ahead.
honestly don't know.
Okay, so we have all these thermodynamic parameters that we've been talking about for the spontaneity of a chemical reaction. Now, remember the second law of thermo. It says that the delta S of the universe has to be greater than 0 for spontaneity. So why can't we just calculate the delta S of the universe? Right? And see what that is. What do you guys think? Ahmed, are you there? Ahmed? Brianna?
Hi.
Hi, what do you think? Should we just calculate the delta S of the universe?
I want to say delta G.
Okay. Now, let me ask you this. Is delta G related to delta S of the universe?
Yes.
Yeah, it is. So we could calculate either one, right? It equals minus delta G over T, right? That was in the definition. So they're related, delta S of the universe. And that's kind of where we get out of looking at universe terms and just look at reaction stuff. And we looked at that before. So we can't forget that. And it's going to come back again and again in electrochemistry. So we can calculate delta G. Now look at the sign. There's a sign change between the relationship of delta S and delta G. So we're looking for delta G's that are positive or negative for spontaneity, for spontaneous reactions. What's it have to be, negative or positive? Check this out. If delta S of the universe has to be positive for spontaneity, what does delta G have to be?
Negative?
Negative. Yeah. So we could calculate the delta G for this to see if it's negative. Now, in this problem, they don't want you to use that. They want you to use those EMFs or those reduction potentials to do this calculation, which implies there must be a relationship between delta G and E cell. And there is. And we'll look at that maybe a little bit later, depending on how far we get. But we see that delta G is negative when E cell is positive. And that makes sense from all the things that we looked at. Remember before, if we looked at an E cell value that was negative, what that told us is that the opposite is spontaneous, right? If the E cell is positive, then that means that for that reaction, where we see some reactant is oxidized, some other reactant is reduced, for that, when it comes out to be positive, then that is a spontaneous redox reaction. Okay, and we talked about that in the last slide in the PowerPoint. Where was it? It's got to be up here somewhere. No, not here. Here we go. So when the reduction potentials are above the Xi, then that's where a reduction is going to take place spontaneously. If they're below the Xi, then it's the opposite. The Xi gets reduced and whatever's below gets oxidized spontaneously. So all the things that we were talking about here are implied, but you haven't had a chance to, study it and think about it yet. So that's why we're discussing this now. So what it turns out to be is because of these relationships between the sign of E, another way to calculate the spontaneity for a redox reaction is just to calculate E cell. So we calculate E cell for this and see if it comes out positive or negative. And then that'll tell us whether it's spontaneous as written or it's spontaneous in the opposite direction, where the electrons flow the other way. Is that clear? Any questions on that? So we want to calculate E cell. And later on, we'll find out that's related to the sign of delta G, which we know is related to the sign of delta S of the universe, which we know from the second law is the law that tells us whether a process is spontaneous or not. Any questions on that? So we want to calculate E cell to answer this activity 1. Okay. Now, since we're just fooling around and we got lots of time, I'm going to ask you guys to do some more work. I hope I'm not asking you too much, but anyway, I'm just going to push it. Now, I see this for activity 1. I see aluminum 3 plus. That has an oxidation state. Does anybody know what it is? How to assign oxidation states? Do you remember yet? Anybody?
I think it's 0.
Aluminum 3 plus?
No, never mind.
Yeah, you what you're talking about is aluminum is 0, right?
Oh,
That's what
because
you're
it
thinking.
has a charge. So if it has a charge, I think it would be 3.
Yes,
And
absolutely
if it's
right.
alone, if it has no charge, it's 0.
Correct.
Okay, cool.
Yep. So now you assign aluminum 3 plus as a 3, iodide is -1, aluminum is 0, and you have I2, which is 0. Okay. And now we want to see if this redox reaction is spontaneous. So I look here, which element is getting oxidized and which one's getting reduced? Can anyone answer that question?
I is being reduced.
Well, if I is being reduced, that means that it's accepting electrons, right?
Or, yes.
So wouldn't it get more negative?
Yeah, so it's being oxidized.
Yeah, very good.
Yeah, it's reversed. And then the aluminum is getting reduced.
Awesome. So this one looks like it's gaining 3 electrons, and this guy is losing 1 each. And yeah, that's right. And so it's a total of 6. Now there's a typo in this. It's not balanced. There should be a 2 right here, right? Right here. Okay, but anyway. Now you guys coming from Chem 200, you know something about metals and nonmetals and their affinity for electrons. Can anybody refresh my memory on metals and nonmetals and their affinity towards electrons? What do they tend to do with them? All right, let me ask another question. Where do you find metals on the periodic table?
In the center?
And yeah, center and left.
Yeah, towards the left.
And where do you find the nonmetals?
On like periods 1 or 1, 2, and like the edges.
And up to the upper right, kind of.
Yes.
So you remember your trends in the periodic table from Chem 200. As you go down a column, things get less metallic. And as you go from left to right on the periodic table, they get more non-metal like. Remember?
Yes.
Yeah, okay. See, all this stuff that you learned in Chem 200, you got to remember that kind of stuff too, because if you've forgotten it or you didn't learn it, then it kind of hampers you in understanding Chem 201 stuff. But that's all right. That's why we go back and look at these things. Now, I have a metal here, aluminum, right? What's iodide? Is it a metal or a non-metal?
A non-metal.
Yeah. It's on the, the right side of the chart. It's over there with bromine and fluorine and so forth. And so now I have a non-metal losing electron. And I have a metal gaining electrons. Does that sound fishy to you guys? Well, it should, right? From your Chem 200, because you were taught that the opposite should take place. Metals tend to lose their electrons, non-metals tend to gain them. They don't give them back. So right off the bat, you should be thinking that this is going to be non-spontaneous. Just from your Chem 200. And so that should make sense. So what we want to do is to calculate E cell for this. Now, we're going to need some values from that reduction potential chart, E cell. And now the E cell, remember the one formula that we can use that we just went over that uses reduction potentials. E reduction at the cathode, where reduction takes place, minus the reduction potential at the thing that you believe is the anode, where oxidation is taking place. So to fit this reaction with this equation, I think you need to pick what is the values for these terms and use that equation. So what is the thing being reduced in this reaction? You already told me once.
The aluminum.
Yeah, aluminum 3 plus, right? What is the thing being oxidized?
I.
I minus, right? Now we don't want the oxidation potential using this formula because we want to just use that one table like in your book. So what do I need the reduction potential of if I want to represent the oxidation potential minus the oxidation potential of iodide? I need the reduction potential of, anybody see it? I2. Right? Because that's what's going to be in the table, even though I want the opposite because in this formula here, it's I minus that's going to I2. Does everyone see that, E cell? Any questions on how I filled in these?
So yeah, so the reason you used I2 is because that's what's like reducing.
Yeah, because at the anode, that's where oxidation takes place.
Okay, yeah, so you don't want that, you want the, okay,
Yeah, so I want the reduction potential. So I took minus the sign here, and now I can replace the oxidation potential with reduction, because in this formula, both terms use the reduction value.
okay, that makes sense, thank you.
Yeah, sure. Any other questions? All right. Now I'm going to need to go back and find that value for aluminum and I2. So I want to look at, oops, go away. Nope, wrong way. Technical difficulties. Okay, here we go. There. Please. There we go. All right. So I want the reduction potential of aluminum, which is right here, minus 1.66, and the reduction potential of I minus, which is right there. So those are the two guys that I want. I looked those up, and I put them into this formula. So I have a minus 1.66 minus 0.54 equals a negative 2.20 volts. It's negative. E cell's negative. That means it's non-spontaneous, or the opposite spontaneous. So by calculating a negative E cell, I know that relates to delta G. So delta G would be positive, and I know that when delta G is positive, the reaction is non-spontaneous as written. The opposite is spontaneous. In other words, aluminum metal will give up its electrons to I2, and that makes sense when you think about Chem 200 and nonmetals and metals. Any questions on that? No? Right. Okay. Okay. All right, no questions on that one. Then we can go to the next. Now, the next activity says draw a diagram and determine the cathode anode direction of E flow and all these other things for a voltaic cell made up of nickel and aluminum. All right. This, I think you guys should really do yourself and practice. And do this as often as you can, because by doing this, this will prove to yourself that you understand how batteries work, and you can apply all the definitions that you need to know for redox. And that deals with, you know, the definition of an electrode and all those other things. So I'm gonna sketch this up real quick for you guys, but you guys should think about it and do this on your own for as many examples as you can. Okay, so this is user hand notation, and I want to draw a cell. So I'm gonna just draw a beaker next to another beaker. Then I need a salt bridge in there. And the salt bridge maintains electrical neutrality, and you'll be making these in lab. In one half cell, I have nickel. So I'll just draw a nickel plate with some solution. And I'll have nickel 2+ ion in that solution. On the other side, I have aluminum. So that's the aluminum electrode. Now remember, electrodes are just solid surfaces which will allow for exchange of electrons. When the exchange of electron is one that something gains electrons, it's called the cathode. When the exchange is where something loses electrons, it's called the anode. But it's just a solid surface. And in this case, both of these half cells have what's called active electrodes because they are both in the redox reaction. I got aluminum here and I got nickel solid here. Sometimes, like for the standard hydrogen electrode, you won't have a solid surface. So you have to supply one, and usually you put in an inactive electrode like platinum. Or in your lab, you're going to use graphite, which is what they use in a lot of the dry batteries. So these electrodes are common. Some are active, some are inactive, and you have to distinguish between the two different definitions. And you know when they're active because they are represented in the half reaction. Okay. Now, when we finish the cell, we usually connect with a wire through a voltmeter the two plates. Now, once I make that connection, and I have the electrolyte over here, aluminum 3+, it's kind of getting messed up there. 3+. Okay. Now there's going to be a spontaneous flow of electrons. Now I'm going to ask you guys, which way do the electrons flow? And once I know which way the electrons flow from which half cell to the other, then I'll be able to write the half reactions involving the electrons that are taking place in those half cells. Does anybody know how I could figure out which way the electrons flow? All right, I'll give you a hint.
Can I figure out which way the electrons are going to spontaneously flow by looking at the reduction potential table? Can I do that? Yes or no? You got a 50-50 chance out there. Anybody feel lucky?
I'm gonna say yes.
Yeah, you are lucky. You should play the lotto. Yeah, that's right. That's one of the purposes of that table. Remember, it's a ranking according to reduction. So the thing on the top is going to get preferentially reduced by the half reaction on the bottom. And so we got to flip that half reaction. So I have to look at that ranking of nickel and aluminum. Now you can go back and look. I'm not going to do it because it's a pain in the ass with my computer and how retarded I am using one. So I'm going to let you go back and look at that. And I think you'll see that the reduction potential, E reduction for nickel 2 plus, is minus 0.23 volts. And E reduction for aluminum 3 plus is minus 1.66 volts. So, which one of those is higher on the chart? Nickel or aluminum? Anybody? Which one's higher on the chart, nickel or aluminum?
Aluminum.
Okay. Let me ask another question. Which number's larger here? Minus 0.23 or minus 1.66? Which one's higher?
Nickel.
Yes, this is a larger number. So it's higher on that chart. So what's your conclusion on which one gets reduced?
Nickel.
Yeah, great. Thank you. Nickel. So nickel's going to get reduced. So I can write over here, nickel 2 plus 2 electrons goes to nickel, which means that the other guy is going to have not reduction, but oxidation. So over here, it's going to be aluminum goes to aluminum 3 plus 3 electrons. Okay. Any questions on that? All right, so by looking at the chart, I know which way the electrons have to go. They come from the aluminum because that's where oxidation takes place. So they're going to go this way. And they go into the nickel because that's where the reactant electrons are going to be. And so now I can name all my electrodes and everything according to the definitions. So the aluminum electrode is where electrons are getting lost from aluminum, and aluminum leaves its electrons behind and dissolves into solution as aluminum 3+ ions. So this must be called the anode, because that's where oxidation is taking place. And it's also given the symbol negative because electrons go away from negative charge. So it seems sensible that it's the negative pole. And we designate the negative pole sometimes with the color black. It's the black electrode, which goes to the other pole, positive, where the electrons are going towards. That's designated as red. And it's called the cathode because that's where reduction is taking place. Nickel 2+ ions are coming out of solution, grabbing the electrons and plating out as nickel solid. All right. That leaves us a few more details to fill out here. And that would be the net redox reaction. I see I have 2 electrons being gained, 3 are lost. What's the least common denominator of 2 and 3?
6.
All right, so I need to change this to a 6, so I'll multiply this through by 3. I need to change this to 6 electrons over here, so I multiply through by 2. And now I'm ready to add them up, so I can cross out the number of electrons gained and lost. So the total balanced equation looks like this. Um, 3, 2. All right. And now I know the charge is balanced because I got a +6 over here and a +6 over here. The only other thing I have to do is calculate the E cell, and I can use these values up here. So E cell equals a minus 0.23. That's the reduction potential for the thing being reduced at the cathode, minus a negative 1.66 volts to give me a positive 1.34 volts. And it has to be positive for it to be spontaneous. If it was negative, that means the opposite is spontaneous, but it's not, it's positive. So everything looks good. Any questions on that?
So this one is like activity 1. You just want us to draw it out.
Activity 2, yes. Okay, any other questions? Now, I have a question for you guys. So this is the voltmeter reading, the E cell value you would expect in a battery made up of these 2 half cells, right? So it's a battery. Now, what happens to this voltage potential as time goes by? What happens to the voltage potential of any battery?
It decreases.
Yeah, it decreases. And it decreases and it decreases until what?
It's dead.
Until it's dead. And so now you know the expression old chemists never die. They just reach equilibrium. Well, they're dead, just like this battery would be dead. So when E cell equals 0, we know E cell is related to delta G. We haven't shown this yet. It's a real simple proof, though. So when E cell's 0, what's delta G?
0.
Yeah, it's an equilibrium. So anyway, that was just a bonus for you guys. Just another little bonus connection. You could send me a check in the mail if you want. I could give you my address later. But any questions on activity 1 or 2 so far? All right, good. You guys got to go back and do these yourself. Don't look at the answers and stuff and study them. That brings us to activity 3. I'll just move this. Out of the way. All right. All right. Activity 3. Now they're giving you an E cell value for the cell made up of indium +1 that goes to +3, so it's getting oxidized, and bromine liquid is getting reduced to bromide. And they want you to determine the reduction potential of indium 3+ to 1+. So this is great exercise using the definitions in the table of ranking. Okay, so essentially for this activity, they're giving you E cell. So E cell, we know, has to equal E reduction at the cathode minus E reduction at the anode. And they said that value equals 1.46. So now we just have to fill in what is meant for these guys and then solve for one of them. Okay, so in this scheme, in this activity, what is the thing being reduced? For activity 3, I have these two. Which one's being reduced? Indium or bromine? Another way I could ask this is, which one has electrons as reactants?
The bromine.
Yeah. So that's the thing getting reduced. And so that's going to be at the cathode. And the thing that's getting oxidized is this indium +1, right? It's losing electrons. But I'm going to be looking for its reduction potential, and it's not the reduction potential of indium +1, it's the reduction potential of what?
The indium +3.
Yeah, you got it. All right, moving right along. In the problem now, they give us the overall E cell, and we can look up this guy from our table, and then we can calculate what they want, which is the reduction potential of indium 3+. And so that's the plan. So I looked this up on the table. I find out that the reduction potential is 1.07 minus E reduction, indium 3+. So that means that the reduction potential of indium 3+ equals, anybody know?
Would it be negative 0.39?
Let's see. I'm gonna have minus reduction. I'll do it in steps. .40. Am I good so far?
Yeah.
Okay, good. Oh, 3+ up there, not here. So E reduction of indium 3+ equals minus 0.40 volts. All righty. Any questions on that one? All right. The last thing that I want to do is activity 4 and 5, and this will be relatively quick, I think, but you're going to have to go back and think about it later. Okay, so for this, for activity 4, it says use the table that we looked at in the notes to predict which is the best oxidizing agent. Now remember, for an oxidizing agent, what happens to it? Anybody?
It loses electrons.
Okay, good. This is confusing, and that's why we want to go over this agent formalism. When something is oxidizes, it loses electrons, but that means that the agent must gain those electrons, right? So it must be reduced because it gains those electrons that it makes something else get oxidized. Does that make sense? It's confusing.
Yeah, it makes sense.
Oh, good. But I mean, it's such a pain in the ass. They have this stuff. I don't know, why do they make it so confusing and things like that? I think what they do that for is because they want to make you slow down, think about the definitions, and apply them in the right way. And to do that, you have to be very anal about each little bit. So now they're changing the name on you. They're saying, okay, this is an oxidizing agent, which is another way of saying this thing must be reduced because it's pulling electrons away from something else. And that's what makes it an agent. So I'm going to use that list where in that reduction list, remember how the chart is for reduction. how was that written as far as the electrons? Are they on the right or the left of the arrow? The electrons are on the
Right?
left. That's okay. It was a good try. You had a 50-50 chance. Reduction means something is accepting electrons, right? So the reduction chart, if you go back and look at it, all the electrons are on the left, right? I mean left. See, I'm even getting confused. Okay, so good. In that reduction chart, the things being reduced are on the left side. And so where are the best ones to be reduced, or the most likely ones to be reduced in that reduction table that we looked at, that chart? Where would they be found? Well, they're going to be found on the left, right? Over here, because those are the things being reduced. Which ones are most likely reduced in that chart? Does anybody remember the ranking? Okay. The ones that are most likely reduced are the ones that are high up and on the left, because when you pair them up with some other half cell, they're going to be above it. And so they'll be reduced and therefore oxidize that other half cell or whatever's in that other half cell. Does that make sense? Should I go back to that table? Yeah, it might be worth going back to the table. Just real quick. So the strongest oxidizing agents are the ones that are best reduced and they're the ones at the top of a reduction potential chart. These guys tend to get reduced by anything below them. So I have to look at that list that they gave me and see which ones. So it's Br2, F minus, or Li plus. So Br2, F minus, or Li plus. All right, so I'll go back to the table and I see Br2 is right here. That's high up and on the left, so that looks good. F minus is over here. If I reduce F minus, then I'm going to get something like F2 minus. And there's nothing here on this table that gives any information about F minus taking on another electron, and therefore it's probably not very probable. You know, F has a full shell. Once it takes on one electron, it's not going to take on two. So F minus is not a good choice because it's not on the left. It doesn't get reduced. It's already reduced. And then the last possibility is way down here, Li plus. That's the least likely being reduced. It's the worst oxidizing agent. Okay. Any questions on that? And then the last one, real quick, is use the table to predict which is the best reducing agent. Therefore, those have to be oxidized. So Br minus has to get oxidized, Li plus has to get oxidized, or copper is going to get oxidized. So if we look back here at this ranking over here on the left, which is the ranking of reductions, and we want to look for the best reducing agent, which means it has to get oxidized, then reducing agents are going to be on the right. So this is where we have to look for it. If it's on the left, then you shouldn't consider it because these guys are already oxidized. They can't lose any more electrons. Okay, so it's going to be on the right and it's going to be the lowest. So it's on the right and it's the lowest. So in that list, we got Br minus, which is on the right, but it's way up here. That would make a terrible reducing agent because Br minus doesn't like to give up its electron. It's a non-metal. They want electrons. The next one is lithium plus. That's over here on the left. That's on the wrong side. If this gets oxidized, we're going to start taking out core electrons, and they're held really tightly, and that's not going to be very likely. And we don't have any information on that kind of a reaction here. There's no lithium 2 plus here, so that can't get oxidized. That's a bad choice. So then we go to copper. Copper is on the right here. It's also here too. But the best one is copper. It's on the right and it's the lowest. So copper in this list is the best reducing agent. I guess copper plus one would be better, but that's not one of our choices. It's just regular copper. It's bromide, lithium plus, and copper. So out of those three, copper is the best. All right, sorry, I went over a little bit. I thought I was going to end short, but we kind of took our time going through this. So now I just would like to open it up for any questions. If not, then you guys should have a good day.